Hello, my name is Tomasz, and I'm a software engineer here at Software Mansion. And I am currently in the Starknet developer tools team, and I've been working on many of those tools. So yeah, my today's presentation will be a very basic introduction to InterPlanetary file system. I had to learn all of this for the purpose of the presentation, so please bear with me, I'm no expert. And starting with the definition, IPFS is a modular suite of protocols for organizing and transferring data designed from the ground up with the principles of the content addressing and peer-to-peer networking. This is the definition taken from the docs of IPFS. And from the definition, we can see that there are two main key points, that the IPFS is based on content addressing and peer-to-peer networking. Content addressing, we'll get into that in a minute, but peer-to-peer networking, you may have heard about it sometime, like something like BitTorrent, downloading a torrents, you may have heard about it. What does it even mean? In the traditional network, it's basically centralized. So if you host a file, you probably host it on like Google Drive or somewhere else, and the server is proprietary to Google. You send a request to the Google server that you want to take the JPEG file, and then you get it as a response. And in the peer-to-peer network, all of the peers or nodes, I will be using the terms interchangeably, are connected to each other, so that they don't have to connect to the one main server. They can just ask one of the peers in the whole network. What are the problems with the traditional networks? The main problem is that it is centralized. So if the server dies, nobody can retrieve the JPEG file, and basically cannot connect to the server. So the data becomes virtually inaccessible, and all of the responsibility to ensure the availability lies on the server operator. And in the IPFS, in the peer-to-peer network, it removes the dependence on the single point of failure. So if one, that's what I was talking about. So if the server dies, nobody can get the file. But in the second scenario, when for example, one of the peers that has the JPEG file dies, and if we are this peer marked as green, we do not have the connection to the peer that died, but still can retrieve the file from the other peer that has the file. What are the other problems? Geographical limitations. So in the traditional network, the data has to be fetched from sometimes from long distances. For example, we're here, and if I wanted to get the contents from the file from, let's say, Australia, and if I have a poor bandwidth, it might take some long time. So it leads to latency issues. In the IPFS, the data can be fetched from the nearest node that has the file. So let's say the nearest node that has the JPEG file isn't on the other half of the globe. So for example, 500 kilometers away. So if I have the poor bandwidth, it will make a huge difference for me. As I said, there is no reliance on the main server. You can just go to any other peer that has that. And one of the other problems is censorship. So in the traditional networks, you can just be banned from using the server. Like let's say you abuse some terms of services of, let's say, AWS or any other cloud service. You might be banned. You won't be able to use it. The same goes for the governments. If they don't want you to use some service or access some data, they might simply ban it. One example of this was Turkey. on 29th April of 2017, the Turkish government banned their access to Turkish Wikipedia. It was probably because of the criticism of Turkish government and some of their other wrongdoings. In the 2020, it was unblocked, but it was still available, not through the traditional network, but it was available from IPFS. So you just had to connect to the IPFS network, and you could simply go to the network to the Wikipedia and access all of it. So yeah, and so you may be thinking, what is the difference between like IPFS and other P2P networks protocols, like for example BitTorrent? So you can think at it like IPFS is like one big torrent. So if you want to download something from the BitTorrent protocol, you have a torrent file and you download the whole file from this torrent. And on IPFS, you can look at all of the network like one big torrent that holds many different files, and you can just download some of them. And also one problem that IPFS solves is that you can, for BitTorrent protocol, you can create many torrents for the same data. They won't share seeders. Seeders are the people that hold the data and allow you to download it from them. And IPFS solves that problem because you don't have many torrent files. The whole network is one big torrent file. So yeah. And the other key point that was marked there was content addressing. And in the classical traditional networks, we are using location addressing. So we are using, you're going to the where it is, where then our resource is. So as an analogy, we can tell somebody that my phone is in my room, go there and get it. And we have like a map to where to go to that room, and we don't exactly know what is the phone what is the exact phone. We know that it is somewhere there in the room. But about content addressing, you know what it is. So like I could tell somebody that here's my phone, a picture of my phone, go get it, and you will go and find it somewhere, like the exact phone. And the problem with location addressing, for example, are that problems with that are that sometimes you go to the URL and you find like there is no such URL, or there is no available content. So there's one example taken from the IPFS blog. So they stated that, for example, when you open the following URL of an image of astronaut Jessica Watkins from the NASA website, rely on AWS servers that host the NASA website. So we might think, okay, some part of the internet is reliant on AWS servers. So we might think, okay, they are pretty responsible, and it should be there. However, later, they state that the file is only available as long as the origin server hosts it. So the problem is when we go to the network when we go to the URL that is under this link, we can find that it is not found. So yeah, the problem is that with the traditional network, you can go to the website and you are there's probability that you won't find the file. Because we are relying on the host, relying on the server maintainers that they will provide the file for us. So yeah, what is exactly the content identifiers in the context of IPFS? So in the URLs, we were, as I said, we were using the concept of where something is. We were going to the URL and we were looking for the part of the internet where we can find it. In the context of IPFS, we have the content identifiers. So, as I said, we find what something is. So we get the identifier of a file that we want to retrieve. This is basically hash and metadata of the file. They are in the form of like v0 and v1, and I will get into that in a second. So basically, earlier the v0, it was the content of the file hashed using SHA-256 with the data was encoded in protocol buffers, and it was all in base 58 BTC encoded. So the problem was that in the beginning it was a good solution, and later the IPFS developers started to notice that it may not be such a good solution. For one thing was that the whole hash was case sensitive. So in the case of browsers, it was fairly problematic. And later they developed the V1 version of content identifiers. And they were developed for the ease of use of other hashing algorithms, for other content representations. So you could use the representation of JSON, not only protocol buffers, and any other algorithms that you wished to use. So the V1 version uses three key concepts: multi-hash, multi-codec, and multi-base. And these are the parts of the content identifiers, parts of content identifier. So the first, multi-hash, basically what it is, you get as I said, you hash the file, so the zeros and ones on the right, and then you glue it together with additional metadata, so what hashing algorithm was used to hash this file, and how long is the hash. How the hashing algorithm is encoded. This is just the top of the list from the multi-hash GitHub repository. And there are many algorithms that are used, that can be used for encoding the data. And for example, let's say if we wanted to use SHA-256, so that would be the multi-hash of the whole file. So in the beginning, so on the top, we would have the 0x12 in hex and this in decimal 18, as in the screen. So we could see the row number 9. The SHA-256 is 0x12. So it is encoded in binary, of course. It is on the front. Later we have 256 as the length of the hash, and then we have the hash. As I said earlier, before hashing, we store data in a particular encoding. So it is another problem that we don't know what the encoding is. So the solution is let's glue it together with another prefix. So this is a data encoding algorithm this time. And also there are many of those algorithms. All of them are available on GitHub. So if we didn't know what data encoding algorithm we are using, so let's say we got the data, we wanted to decode it, and we assumed it was encoded in protocol buffers, and it was actually in JSON, we will get weird things. Another problem, so future-proofing, giving a CID version. For now, version 1 is used here in the CID v1. It allows for any other possible standards in the future. So yeah. And another problem that we encounter here is that we don't want to store it all, the whole content identifier in binary. So we might want to store it as a string. And for example, we might want to encode we might have a representation like 11111, and this could be a valid string in base 2, base 4, base 8, base 16, base whatever. And when we are decoding the hash, the content identifier, we would like to know what base it was using. So yeah, as previously, we just glue it together with another prefix. So this time, in this example, the prefix would be p. And from the screen, also from the GitHub repository with the spec, it means it was in base 32. There are, like you can see, many of those possible encodings. It also is only at top of the list. So there are many possibilities, and it means that if you want to encode some data, and you will be using, you can use many different algorithms. You can use many different possible encodings, and there can be many different hashes, but they may just point to the same file in the IPFS, because that's just basically different encoding. So how can we add a file to IPFS? For the beginning, in the beginning, like the file is chunked for the ease of storage. It is split into 256 kilobytes of data, and it allows for easier storage. Sometimes the chunks are the same. Like let's say in this example, we had this one big file, and it was split into the 4 smaller ones, and the first and the third one are the same. So for the problem of we can just address the problem of duplication here by just simply forgetting the third one and just encoding it as three pieces of 3 blocks, not just 4, because that would be, if we stored the 4 blocks, it would be redundant. So yeah. And if also, supposing that we have 2 similar files that, for example, share most of the bytes, and I have one of them and I want the second one, we can just download one of the chunks that are missing. So you just need to download the different bytes. Also, the data is immutable, and once stored, the hash of the particular file will not change. It always will be the same. So same file uploaded. If you wanted to upload the same file twice, it would be only stored once, because the IPFS would get only one hash, the same hash. So the file wouldn't be stored twice. And how it is also stored in IPFS? It is stored as a unique FS file. And it is a protocol buffers-based format for describing files, directories, and symlinks in IPFS. And it is stored as a Merkle tree. So basically, under the hood, there are everywhere hashes, and they are based on hashes. But the whole concept is that the file is split into chunks, so that the bytes 0 to 200 are on the left, 200 to 350 are on the right. And so on and so on, recursively, they are split until the base is reached. But actually, it isn't a Merkle tree, it's a Merkle directed acyclic graph, just for the purpose of the duplication, like in the example before. Also, if you wanted to upload the directory to the IPFS, it would be very similar. We just need to know how to map the files to blocks, and we just do it by mapping the mapping file names in the directory to the hash mapping file names in the directory to the blocks using hashes. And what about the data that we get from that we get from the IPFS? So if you're running a node, the data is cached of course, we can reach it sometime, but the storage space is finite, so we may not store everything that we get, everything that we want to upload. So the nodes are using garbage collection, and there are many different algorithms used for that, but you sometimes may not want to destroy all, delete all of the files that you have on your node, and you can protect the data simply by pinning it, and then the node will not be deleting the data that you are storing on your node. And on the other side, we have getting the data. So let's say we are the node and we want to get the file that is which content identifier is QMCAT. So what are we trying to do? We have to send the want list. What is want list? Want list is this is a simple description of what it is, but it mostly contains that content identifiers that we want to get from the network. And here simply it looks like almost like JSON, and we have the content identifier and that we want it. So yeah, how does it work in the network? So for my currently connected swarm of nodes, I can trade data with each node from this swarm, and we can choose the node that has data, and we send the want list to the node. Basically, you send it to every node in your swarm, and some nodes reply that they have that, they have the content, but some others say they don't have, and we later send the want list to those that have the data. Then the node, as I said, it checks if it has the file. If it doesn't, it responds that it doesn't have the file. And then if it has that file, it decides whether it wants to send it or not. It is also based on that fact that sometimes there are many leechers. Leechers are nodes that simply retrieve that want the data but do not share anything. But there are many algorithms under the hood that are working on that. So yeah, later if the node decides to send the file, then it is sent back to me, for example, and then we check if this is the right file. How can we do that? When we get the block, the file, or the data that we wanted, it's encoded somehow. We get the content identifier of it. So we using the fact that it was somehow encoded, like using some algorithm, let's say SHA-256, we can check how it was. It is actually the right file. If it isn't, we just go to another node. If it was, we then send the cancel request that tells other nodes that they shouldn't just keep sending the file if they have it to me. If the cancel request isn't reached, it doesn't reach in good time, so the other nodes keep sending the file back to me. If I have it already, the node will just drop it. So the whole algorithm is called bitswap. You can learn more about it on the IPFS documentation. And also, there's a thing that we can store that what files have. We can tell that what nodes have which files in our network, and this is simply stored in a hash table in like key value pairs. But there's a problem that we cannot store every piece of data that is in the network because the hash table would be simply too big. So the solution for this is distributing all of those tables to many different nodes from the network. So the simple overview of this is that you base the data that is, you base where to store the data based on the prefix of the data and the node identifier. So let's say if we wanted to store QM full, we could store it in the QM footage node. This is just an example here. So how then we get to find who has the data? So if we, let's say, have QM full, we then find the node that is responsible for the info holding the info who has QM full and tell him that we want it. So if we want QM full, we then find the node and get the info who has the file. So what is happening when in all of our network in the swarm of the nodes that we have, there isn't a node that has the QM cat, for example, QM cat content identifier. So as I said, it is based on the prefixes of the nodes and the contents. So let's say that we had a QM city in our node swarm, QM city node. So we would go and ask the node, do you have QM cat? And he would, for example, didn't have it. So he would reply, no, but I know QM cola. And then QM city would ask QM cola if this node has QM cat. No, but it knows QM Kate, another node. So then, this one. Then QM Cola would ask QM Kate if it has QM Cat, and let's say if it has, it would reply yes, I do, and then it would just send QM Cat to me as a chain of after the chain of requests, and then what would happen? Just this flow that I just described. So we would get if we decide if the node wanted to send it. If it sent it to me, then I would check the contents of the file and the hash, and then we'll set cancel request, and so on and so on and so forth. This is based on Kademlia algorithm. It was used for the distributing the hash tables from over the network. Yeah, it was just a basic overview. There are many more things going under the hood, and yeah, if you want, you can check out the white paper on the algorithm. So what about Filecoin in all of the IPFS? It is an incentive layer over IPFS. What does it mean? If we just join the network and we have to store the files, it may not be good for everybody, because we might be greedy. So we might not want to store everyone's files. Not everyone does it voluntarily. So it is an incentive over the IPFS to store the files. You basically rent your free space in exchange for Filecoin for Filecoin from other users. And basically, you rent your the person who is using your free space is giving you Filecoins. You are basically a miner if you are renting your free space. And Filecoin uses proof of replication and proof of spacetime. What is proof of replication? The server proves to the client that it allocated a certain amount of storage exclusively for storing the copy of the file that it requested, and it also means that data can be easily accessed because of the proof. And proof of spacetime, and it is used for the storage providers that they are continuously storing the files, their data over time, and not simply discarding it. And periodically, providers create and submit those proof of spacetimes to prove the data is still being held and wasn't altered. So yeah, if you want to use IPFS and get some money from it, you just can become a miner. So you can just run your node in the meantime on your laptop every time it is on.